So today our webinar about design and simulation of a differential mode wideband bandpass filter. So my name is Alex. I'm going to offer you this webinar this afternoon, and sorry again for the delay in starting the webinar. We're going to offer you this webinar based on this agenda. So first, I'm going to give you a quick introduction regarding the design and the structure. Then we're going to see the software in action, and then we're going to have a question and answer session at the end. So as we said, the webinar is about the differential mode wideband bandpass filter. You know that in the world of the microwave engineers, developing a balanced RF front end is an ongoing challenge. So one of the most essential components in the high-speed wireless communication system, due to their higher immunity to the environmental noise and low electromagnetic interference, is the differential bandpass filter. And most of them on-chip systems rely on differential mode operation with good common mode suppression. In this model that we're presenting today, we're going to talk about a wideband differential mode bandpass filter with a good common mode suppression, which is designed on a microstrip line with open stops to achieve a wide differential mode differential mode pass band and common mode stop band, of course. The bandwidth of the structure will be about 60%, which is centered at 5.8 gigahertz. So you know these days, like the 5.8 gigahertz is the very hot frequency, since it's also approved by the ASM, and a lot of applications these days are operating in this frequency. And it does have two symmetrical bisections of two-stage branch line topology. And we're excited with differential and common modes. So we're going to use the do of SolidWorks and HFWorks to present this structure today. You know, SolidWorks is probably the most powerful 3D CAD in the market right now, and HFWorks is one of the most powerful three-dimensional electromagnetic solvers. We use the SolidWorks as our CAD to draw our model, then we use HFWorks as our high-frequency solver to simulate this model. So without further ado, let's go to see the software in action. Here is the filter that I was talking about, and as you can tell, this is our substrate that we have printed our strip lines on top of this substrate. The differential signals are actually presented here. The one that I turned it blue is going to be our plus signal, and this one is going to be our minus signal. If you want to be more precise, in our model, we do also have an air box here. Since we're trying to model the fields, we would like to model the air around the structure as well to make sure that we are considering all the elements in the signal integrity. So here, the model is open inside SolidWorks. As you see the parts, here is the full assembly. It has two parts, and you can actually customize the model as much as you want, change anything that you want. And after you are done with creating a three-dimensional model, simply by clicking this HF tab, you open HFWorks, which is part of SolidWorks. As I said, this do HFWorks is an add-in inside SolidWorks. So simply, you can start to simulate the structure by defining a new study. HFWorks offers three types of studies: parametric studies, resonance studies, and internal study. Each of these studies will have some options that we can choose from. We can choose a multi-core direct solver, or multi-core iterative solver, or simple direct solvers or iterative solvers. Of course, this multi-core feature is one of the features that we embedded inside the software to make sure that you can use the capabilities of your PC to have the faster simulation and obtain your results as quick as possible. You can also have high accuracy or normal accuracy. As you know, HFWorks is based on finite element method. So if you use the high accuracy, we will use higher order elements to simulate, to run your simulation. So the accuracy with the same number of elements will be higher than normal accuracy. You can also obtain higher precision and higher accuracy by refining the mesh or adding more elements. So we'll talk about it later. You will also have the option to do parametric studies, to do adaptive machine, and to compute the breakdown voltage that we'll talk about. Then you will just simply choose the range of the frequency that you want to simulate the structure in. So we can have the option of discrete sweep and fast sweep. Let's say you say fast sweep. Discrete sweep solves the full scale problem at all frequency points. Fast sweep only solves the full scale problem at an expansion point and gives you an approximation for the rest of the band. But at disadvantage that you're going to have a much quicker simulation. So you will choose, let's say we're going to simulate this from 3 gigahertz to 10 gigahertz. And let's say we need 70 frequency points. So it will calculate the steps and it will choose 6.5 as the expansion point for the middle frequency. So of course you can also compute the TDR, which is a very interesting function. So if you want to find the time domain results, you just click compute TDR and you will have this computation as well. After you define your study, the pre-processing is just gonna be done in 3 simple steps. Step 1, you're gonna choose your materials. So for example, in this case, we have an air box that we click and say apply material. So we have a big library of materials, the cable, ceramics, semiconductors. You know, each of them are so many materials that are used in high frequency industry. So you will choose any material that you want to use, any substrate, anything, any kind of metals here. So this one, of course, we just want it to be air. We have also some favorite materials which are easy, just click air. The second one is this part that is our substrate. So in this case, our substrate is FR4EG150. We just chose it from our library. We went to apply the material and we chose the substrate from our library. So the materials are allocated, both materials. Then after applying the material, step 1 is done. The second step would be defining the boundary conditions, or you might know this as the loads. You're going to assign the loads. Here, it's a filter, right? So we're going to have an input port and output port. So port 1, say this one. Here, we define it as our port 1 because the excitation will happen from this side. And port 2. How to do it? We just simply click on boundary conditions. We define port, we choose port. And after we chose port, we select the faces that we want to assign as a port, as simple as that. And we choose our ports. Then, for example, these traces that we see, we want them to be copper. So we can either choose in the material, we can choose them to be copper, or we can assign the perfect electric conductor, PEC, this one and this one. Or no, if you think that they are not perfect electric conductors and they are imperfect, we can choose imperfect electric conductors here. And in this, you can define your surface roughness. Also, I have chosen this side, the left side strip to be my positive signal, and this one to be my negative signal here for this differential bandpass filter. So I chose my loads. Simple as that. This third step of the pre-processing, which can also be done automatically, so you don't have to do it yourself, is the meshing. For the advanced users who know the basics of the finite element method, it's better to mesh the structure yourself. You know that simply by clicking on create mesh, you can choose whether you want a fine mesh or you want a coarse mesh by just moving this bar. But you can also define a lot of mesh parameters yourself for more advanced users, smart meshing and everything. But there is a neat feature here that you can apply mesh control on some certain surfaces that you might think that you do know that you need to have finer mesh. For example, here is a port and it's a pretty small face, so you can apply a mesh control in which you can define what faces you have in your mind and also define your control parameters. In this case, it's the element size. You can say if your global element size is, for example, 6, for this one you make it the 0.3 because you know that you want smaller element sizes for this particular surface. So for example, for this study, I applied mesh control to these traces and also to these 2 ports. If I show you the mesh now, so this is the mesh. You see, the mesh is coarser in the other surfaces, but here at this particular point, the mesh is finer. Or if I can hide the mesh, and if I just hide the air box, just want to show you the mesh on the traces. I simply show the mesh. You see, on traces, we do have a finer mesh, which will guarantee a higher accuracy here. So then we'll simply run the study. You can just come here, run. Even if you don't mesh it and just click run after the second step of the pre-processing, which was the boundary condition assignment, and you click run, it's going to mesh your structure automatically and it's going to run. After you run the structure, it takes like 2 minutes to run and solve the problem. Then you will have access to the results, which is the post-processing part. You will have all kind of the results that you can think of. The first simple thing, you will have a result table. So it will give you all parameters that you can think of in a tabular format. Generalized S matrix, renormalized S matrix, impedance matrix, admittance matrix, the port results, the VSWR, and at all frequencies, okay, within the frequency range, you will have access to all these results. Of course, you can print them, you can export them to Excel sheets, wherever you need. But we would like to see the plots, of course. So the 2D plots, the Smith chart, let's say I want to have a 2D plot. I want to take a look at my S11. S11 differential port. You add it here. Here is your S11. You see? So of course you can also export this plot and take a look at it outside, or you can have superpose two plots together. For example, you say I want to see S11 add, and I also want to see S12 differential port 1. You can add this one, and you want to look at both of them together. You see, now you can see both graphs together at the same time. So you can also take a look at the Smith chart if you want. Set for the Smith chart for S11. Yes, Smith chart for this one. There you go. And as I showed you, you can take a look at it at common mode and at differential mode. Like here, that was the differential mode. You can take a look at the common mode, like S11 of common 1, common 1. Okay. Here will be your S11 in the common mode. So this was this plots were the 2D plots. If you want to take a look at the 3D plots, for example, the electric field, how it works, simply come here and say I want to have 3D fringe plot or vector plot. For example, the fringe plot, there you go. Here is your 3D fringe plot. So you can simply animate it versus space, for example. And you can see the movement of the electric field over here. And this one is the vector plot. You can plot it like as a vector plot. So you can animate this one as well. Not only you can animate the results, you can also do different kind of clippings. You can have a section clipping, ISO clipping, you can do overlay. So you can probe to see what is the field at any point of the structure. And at the end, you can also, of course, you can look at the magnetic fields as well. You can look at the port fields as well. And you can create a report. Simply, you can just go here, generate a report, and choose what you want to be in the report, like the cover page and introduction. So you can write anything, like you can say, here is the report for the webinar of April 12th, for example. So also the model view, you can choose, for example, the current view. You can choose the back view, for example, you add. You can choose the isometric view and add with the mesh. And you can, if you want to include the materials, for example, you don't need the study, the result table, we don't need, let's say. For example, you don't need the file information, you just unclick. You don't need an appendix, unclick. Whatever you need, you can write here, description, here. And just you can have the option to have HTML or Microsoft Word. So let's say Microsoft Word. I just click. So it's going to create a report for me right here, so I can share it with my colleagues they don't have the software available. You see, it opens the Microsoft Word right here in the SolidWorks. See, here is my report. So here is the report for webinar of April 12th, the one that we just wrote. Here are the models. And it shows the material that we applied and everything. And also it shows the electric field, like all the plots that we opened will be shown here. So because the software will automatically know these were the parameters that we were interested in. So it's going to include them in the report. It's going to make it much easier to share it with our colleagues or with our management or everything. At the end, I would like to let you know that if you like to try the software, simply shoot an email to support@emworks.com and you're going to have access to a free trial to try out the software. We will be very happy to send you the free trial version for 2-3 weeks, 1 month, so you will have some hands-on experience with the software yourselves. Thank you very much. Enjoy the rest of your afternoon. Have a great day. Bye.